We're going to take a look at a few problems that involve medians and altitude, of triangles. And the first one looks like this. It says simply find the distance from A to D. Now, if I look at this diagram, a couple things I want to pay attention to. First of all, I see that I have this point of concurrency right here, where three different segments are meeting. And I might want to notice that those segments are all medians. How do I know they're medians? Because each one is going from a corner and it's going across to the point on the opposite side that's dividing it into two equal parts. That would be the midpoint of the opposite side. So this segment right here is going to this point, which is dividing segment AC into two equal parts. We got a segment coming from the corner at C going across to the opposite side, dividing that segment AB into two equal parts. And then we have our segment AD, which is coming across from this vertex, going to point D. Point D is a midpoint because we can see it's dividing segment BC into two equal parts. So AD is a median. I'm just going to write that out. Segment AD is a median of triangle ABC. And so what that means is that point of concurrency, E, is the centroid. And that centroid divides each one of these medians into two parts, but they're not equal-sized parts. We can see there's the big part here, segment AE, and then this little part here, segment ED. The way I think of this is that this big part is going to be twice as long as what this little part is. Or this little part is half as long as this big part. Or we could even say that the big part AE is 2/3 of the entire length of this median. So there's a kind of a lot going on there's a lot of ways that we could view what's happening in this picture. I prefer to look at it this way, that the distance from A to E is going to be 2 times the distance from E to D. And if I'm supposed to find the distance from A to D, what I can do is I can find both of those parts of segment AD, AE and ED, and then I can just add them together, right? So if I fill in, maybe I'll put an X here. I don't know how long ED is. And I'm going to fill in 21 for AE and X for ED. Then it's pretty clear that if I want to find out how long ED is, I can just divide 21 by 2, right? And I get 10.5 for X, which was the distance from E to D. And now the distance from A to D would just be take the distance from A to E and add the distance from E to D. So that's going to be 21 for the distance from A to E plus 10.5 for the distance from E to D, and that's going to give us 31.5 for the distance from A to D. Now there is another way you could do this, which is maybe a fewer steps but involves working with a fraction. We can set this up to say that AE is equal to 2/3 times the length of AD. The theorem that we would have learned for the location of the centroid says that it's 2/3 of the way from the vertex to the midpoint of the opposite side. So the distance from A to E is 2/3 of the distance from A all the way to D. And then what we could have done is we could have filled in our 21 here, and we could maybe say AD is a variable like Y, and then we could say Y would be equal to 21 divided by 2/3, which is the same thing as saying 21 times the reciprocal 3/2, right? Because when we divide by a fraction, we're multiplying by its reciprocal. That's something we would have learned back in like 4th grade. And if I take 21 times 3/2, I'm going to get 31.5. That's just another option for how you could have done this problem. I think this way is just a little bit simpler, mainly because it doesn't involve using a fraction like 2/3 and having to flip it over and multiply by the reciprocal and do all that stuff. I just think of, all right, E is the centroid. It's divided segment AD into the big part here and then the smaller part here. And that big part is 2 times the smaller part. And then we can fill in all our information. That's how we could find out that AD is 31.5. In any case, let's take a look at another example where we are again finding the distance from A to D. We have a similar picture here. It's pretty much almost looks identical to this, only maybe oriented a little bit differently. And now we have our centroid here at E, and we know how long ED is. It's 12. And we are supposed to find out how long AD is. So again, we can say, well, AD is equal to AE plus ED, and AE is equal to 2 times ED, right? This AE is double the length of this short part. And so now if I actually start here and I can say, well, AE is equal to 2 times 12, right? The length of segment ED is 12. 12 looks a little funky. Let me just write that a little bit better. Then I can say that AE is equal to 24. Come back over here and I say, okay, AD is now 24 plus 12, which is going to give me 36. So AD is equal to 36. Again, I could have done that with using this idea, but I think this way is just a little bit easier and faster. Okay, so now we have one other problem that we're going to look at that has to do with altitudes, because what we're doing is we are finding the orthocenter of a triangle. And remember, orthocenter is the altitude concurrent point. So it's point of concurrency for the altitudes of a triangle. That's what the orthocenter was. So it wants us to know the actual coordinates of that orthocenter. And our triangle has these vertices. So let's first go ahead and put our triangle on this graph here. We have point A at 0, 0. Point B is at 10, 4. And point C is at 8, 9, which would be up here. So we got point C there, point B there, and point A there. So our triangle looks a little bit like this. If I can draw that triangle with fairly straight lines. There we go. Okay, there's our triangle. That's not too bad. So we need to find now the orthocenter, the location of the orthocenter for this triangle. So what can we do? Well, we know that the orthocenter is the point of concurrency for the altitudes. We know that each altitude for this triangle is going to start at a vertex, and it's going to go towards the opposite side and make a 90-degree angle or be perpendicular to it. So if we can find the equation of two of those altitudes, right? If we look at those altitudes like lines on a graph, we know that they should have an equation. Every line that's on a graph has an equation that describes it. If we could find out the equation for two of those altitudes, we could solve that system of equations to find the place where they meet. Technically, the orthocenter is where all three altitudes meet, but if we just know where two of them meet, then that's also going to be obviously the place where the third one would meet too. So if we just kind of outline our plan here, we are going to find equations for two altitudes, and then we are going to solve the system of equations. That's right, solve the system, meaning the two equations that we find here. So how are we going to do that first part? How are we going to find equations for two of the altitudes? Well, think about what we know about the altitudes. Again, they're going to contain a vertex, and they're going to be perpendicular to the opposite side. So if we look at, for instance, if we want to know the equation for the altitude that's going to come from A, we know it's going to be perpendicular to segment BC, which means we could find that altitude slope by finding the slope of segment BC and then looking at its opposite reciprocal, using that idea that perpendicular lines have slopes that are opposite reciprocals. So let's do that real quick, and I'll show you why I'm doing it. So first, I'm going to find the slope for segment BC. Remember, little m stands for slope, so this is the way I kind of denote that I'm finding the slope of segment BC. Well, B again was at 10, 4, and C was at 8, 9. So I'm going to do y2 minus y1 over x2 minus x1, or I could just do rise over run. Maybe that would be an easier way of doing that. Let's just do rise over run, moving from C down to B. So to get from C to B, I have to go down 1, 2, 3, 4, 5. So that's going to be a -5. And then I have to go Once I go down those 5, I go over 2, and that's in the positive direction because I'm moving right. So it has a slope of negative 5 over 2. So the slope of the altitude from A, slope of altitude from A will be positive 2/5, right? The opposite reciprocal of negative 5/2. It will also contain point A, which is 0, 0. So if I want to know the equation of the altitude from A, I can use, remember, the point slope form of an equation. Y minus y1 equals m, or the slope of the line, times x minus x1, where x1 and y1 are the point that we know is on that line. So the altitude from A contains point A, right, because altitudes always go through a vertex, and has a slope of negative 2/5, right, has a slope of negative 2/5. So my equation for that altitude would say y minus 0 equals 2/5 times x minus 0, because 0, 0 is going to be x1 and y1. Then if I just kind of clean this up, it actually just says y equals 2/5 x. So that's one of my altitudes. My altitude from A has this equation. Now let's go ahead and find maybe the altitude from, let's find the altitude from C that goes across to, actually let's do the altitude from B. We'll do the altitude from B that's going to go across and be perpendicular to segment AC. So first I need to find the slope of segment AC. So I'm going to find the slope of segment AC, and I'll do rise over run again. This one looks like it has a positive slope because it's uphill from left to right. It looks like it goes up 9, so it has a rise of 9, and then it goes over 8, so a run of 8. So that's the slope of segment AC. The slope of then the altitude from B would be negative 8 over 9. And then the altitude also contains point B, right? So in that x1, y1 would be 10, 4. So if I now want to find the equation of the altitude from B, it's going to be y minus 4 equals negative 8 over 9 times x minus 10. And let's go ahead and, well, let's see, do we need, yeah, let's go ahead and convert this into slope-intercept form, get it into that y equals x plus b form. So first I'm going to distribute that negative 8 ninths, say y minus 4 equals negative 8 ninths x plus, it would be 80 over 9. And then I'm going to add 4 to both sides. So that's going to say y equals negative 8 ninths x plus 80 over 9. Okay, so let's do this off the side. 80 over 9 plus 4 means I'm going to do 80 over 9 plus 36 over 9, because 36 over 9 is equivalent to 4 with the 9 denominator, which we need. We're going to add these fractions. That's going to be 116 over 9. So there's my two equations. This one's a little bit ugly because it's got some fractions. Y equals negative 2/5 x, and y equals negative 8 ninths x plus 116 over 9. So next thing I need to do is solve this system of equations. Luckily, I have two things that equal y. And so what I can do is I can essentially set this part equal to this part, because they both equal y. So I'm going to do that maybe off to the side over here. I'm going to say 2/5 x equals negative 8 over 9 x plus 116 over 9. So now I need to solve this equation. I can either do it by just dealing with the fractions that are in it, or I can do a little trick that you would have learned back in Algebra 1 that would get rid of all my fractions. I'm going to choose to try and get rid of all my fractions at the beginning. The way I'm going to do that is I'm going to multiply every number in every part of this equation, every term, by the common denominator of these fractions, 5, 9, and 9. So my common denominator would be 45, right? That's the smallest number that is divisible by both 9 and 5. So when I multiply every part of this by 45, watch what happens. So I'm going to take 45 times 2/5 x equals 45 times negative 8 over 9 plus 45 times 116 over 9. And the reason why this is going to work out is because right here I can cancel the 5 with, I can divide basically 45 by 5 and turn it into 9. And then 9 times 2x is going to give me 18x. And then I can do the same thing here. I can take that 9 out and make the 45 into 5, right? Dividing it by 9 essentially. And that's going to be negative 40. Oh, there's supposed to be an x right there. That's going to be negative 40x. And then the same thing will happen here. And I'll be doing 5 times 116. That's going to be 580, I believe. And then I can add 40x to both sides. And I have 58x equals 580. And then if I divide both of those by 58, then x equals 10. So the x-coordinate of my point of intersection between these lines is 10. Now to find the y-coordinate, I'm going to plug that 10 right back into here. And I'm going to say y equals 2/5 times 10, or instead of 2/5 times x, I'll make it 2/5 times 10, which is going to be 20 over 5, which is equal to 4. So it appears as though my orthocenter is at 10, 4. But wait a minute, that's point B. Is that possible? Is it possible that my orthocenter is actually one of the corners? Well, if you remember, right triangles, the orthocenter is at the vertex of the right angle. Is this a right triangle? Could we have figured out that that was where the orthocenter would be way back at the beginning of this problem by just realizing this is a right triangle? It kind of does look like one, right? Looks like this might be a right angle. We already know that this has a slope of negative 5/2. Does this line have a slope of 2/5? Let's look. The rise over run would be go up 1, 2, 3, 4, right? So this would have a slope with a rise of 4 and then a run of 10, which is 2/5. Hey, we could have realized way back at the beginning of this problem that this is actually a right angle because these two sides are perpendicular to each other. So it does make sense that the orthocenter would be at 10, 4, right? So maybe I'll just write it out here. Our orthocenter of triangle ABC is at 10,